All right, so now we will start with the second chapter. And the first part of the second chapter, which is actually all about atomic structure and nomenclature, is we will start with what is the atomic structure. Okay, so we as chemists, we are curious people who want to know what everything is made up of, and the same thing happened with the matter also. So we've talked about matter before, as matter is anything that makes up uh, has some mass and has volume. And so we want to know what it is all made up of. And actually that started a long time ago also with Democritus, a philosopher. And he wanted to know what everything is made up of exactly. And he proposed at that time that, matter is made up of very, very small particles, indivisible, right? Things are a little bit different now, but even that time they were considered to be indivisible. And so giving all of that beginning, now so many hundreds of years later, we have a little bit better understanding of the structure, and we're still trying to understand the atomic structure. It's not completely all done, so we will keep learning about it. So that's what we are going to kind of do in this chapter. Okay, so let's go on. And so the first scientist who kind of thought a little bit more about the atomic structure was Dalton, and he's an English scientist, and what he proposed were a few of these things. Okay, so let's go over them. And so he said that all matter is composed of indivisible atoms, which is kind of what the Greek philosopher also said, but it took so many hundreds of years before anybody looked at that again. All right, so but anyhow, so all matter is composed of small, indivisible things called atoms. The atom is a very, very small particle, and it retains its identity during chemical reactions. Okay, so we will talk about the identity also, what we say when we mean that we're talking about a certain chemical, right? So when we say we have sodium, how does it retain its identity? We will talk about that, but it retains its identity in chemical reactions. Okay. And then we say that an element, so for example, again, sodium, it will have all the same kinds of atoms in there. Okay, so that's what he said, is an element will have atoms in there, and all those atoms will be the same. Now, this theory was challenged a little bit, but we'll talk about that. Okay, so not completely all wrong, but there were some things that were added in there. Then we talked about a compound, and a compound is composed of two or more elements in which they are combined in a very specific proportion and also in whole numbers. Okay, so when something is combined, it's combined in a ratio of 1:2, for example, not 1:1.5 or 1:1.75. That's not how it is. It's always like 1:2 or 2:3, something like that. Okay, so that would be a compound combining in whole ratios. And then there is a chemical reaction in which a rearrangement of atoms occur. And what he means by the rearrangement of atoms is that if you start with these number of atoms, you will end up with the same number of atoms. Maybe they are not in the same way, maybe they are combined in a different way, but you will have the same number of atom. And this is also called the law of conservation of matter, okay, which is that matter cannot be created and it cannot be destroyed. All right, so whatever number of atoms you start with, you're going to finish with that as well. Okay, so nothing, no addition, no subtraction in the middle. So then he came up with two other laws, and the first law is that there's a law of definite proportion. And what that really means is that you can take the same sample of compound, or you can take the same compound and you can collect it from anywhere. Okay, so for example, this one is for carbon dioxide, which carbon dioxide is CO2. So no matter where you take it from and how much you take it, ultimately, okay, the ratio of oxygen to carbon is going to be 2:1, always going to be like that. Okay, Whereas in the case of carbon monoxide, which is CO, no matter where you take it and how much you take it, it will always be a ratio of 1:1. Okay, so that is how much it will be, no matter where you take it from, whether it's from USA or Antarctica or India or from, thousands of years ago, it doesn't matter. Okay, the proportion will be the same, and that's called definite proportion. So, or the law of definite proportion. The other one is called the law of multiple proportions. And what that means is that when you take something like carbon dioxide and carbon monoxide, their ratio will always be 2:1 for the oxygen, okay, in there. So if you have two samples, then, or two different things in there, they can be combined in a different ratio, but it's always going to be fixed also. Okay, so again, it's not like, 1.5 to 2. That's kind of what we're saying. And then also what we're saying here in the multiple proportions is that elements can combine in different proportions. So for carbon dioxide and carbon monoxide, the proportion is CO and CO2, right? So 1:1, 1:2. And so they can combine in multiple proportions, but they also combine in a fixed proportion or definite proportion, is that the CO, no matter where you take it from, it's always going to be 1:1. Okay, so that's kind of what these two law means. And this means a lot, okay, because that shows us some consistency in how things will combine with each other. So then let's talk about the atomic structure, okay? Because given all of this, and I'm not saying everything is happening chronologically, but generally things happen in a chronological order. Some things happened consecutively, and so it's or concurrently, I should say, not consecutively, concurrently. So, things, because everybody is working on the same kind of problem, sometimes. So anyhow, so atomic structure was then eventually discovered, and then it was found that there are three particles in it, the electron, proton, and the neutron. And so the atomic structure is made up of these three things, but okay, there is a nucleus, okay, in there, and that nucleus is going to have the protons and the neutron, and outside is where you find the electrons. Okay, that's kind of how it is. So these two particles are found in the nucleus, electron is found outside. This is kind of, the slide here gives you an overview of what's coming ahead, okay, because I'm going to talk to you a little bit about how all of these things were figured out, because this one gives you already, it kind of like, the mystery is already gone, right? We know what's going to happen, so we just need to get there, which means like we're discussing, of course, the history of something. The mass of these particles is given to you over here. Now I've written AMU also because we talk a little bit about AMU sometimes, and AMU is atomic mass unit. So what this shows you is that the neutron and the proton is the same mass, which is 1 AMU, or equal in mass, and you can see that in the gram weight also. And the electron is really, really, really small, okay? And look at the ratio, AMU ratio, right? So 1 is to 0.00. So when it's in the thousandth, or I should say the nucleus and the protons are 1,000 times heavier than the electron. Okay, and then look at the gram weight. Okay, see how small this is. So these are very, very small particles. All right, and so then there's a charge also associated with them. Neutron is neutral and proton is positive and electron is negative. So that is how it is. It took a really long time for scientists to figure out all of these three particles, and actually they are considered to be many more particles in an atom, and they're still finding those. Okay, but this is kind of the beginning. This is the overview, okay, of how it goes. So first of all, the discovery of the electron. It was discovered by J.J. Thomson in 1897, and what he used was a cathode ray tube experiment, and you may want to go see that over here. It's really fun to see how he worked on it. And what he really was trying to figure out is, what is it in an atom? And he found some rays that came out which were negative, okay? And it didn't matter what kind of element he took. He started with hydrogen gas. Everybody kind of starts with the hydrogen gas because it's the lightest gas, and it's nice to be consistent, okay, with what you're studying. So everybody starts with hydrogen gas because again, it's the lightest one, it's the first one, and you start with that. And then he found out that these rays actually were negatively charged. Okay, and you can see that in the experiment and how it bends and all that. And then what he discovered, actually, what he calculated in there, was the mass to charge ratio, okay, of the electron. He called the particle electron, okay, that was coming out, that was negatively charged, and he said there must be something in there, and so that he called then the electron, okay, and this was supposed to be then the mass to charge ratio. Once he did that, then Robert Millikan, he did what is called an oil drop experiment, and he figured out the charge on the electron. Remember what J.J. Thomson did? It was mass to charge ratio, and what Millikan did was figured out the charge on the electron, and this was his experimental design. Okay, this is kind of what he was working on. So you look over here, and then there is an atomizer which will drop, ions through oil, and really literally it is dropping through. Okay, it's a little bit of a complicated experiment, okay, but then using all of this, what they were able to figure out then is the mass of electron. Okay, because okay, fine, there is an electron already, but what are the properties? So they already know it's negatively charged, they know what the charge is by using this experiment, and so then they figured out the mass of the electron, which was very, very tiny mass. So then if there is a negative, then there should be a positive also in the atom, and that fell on to Rutherford. Okay, so he was also working on the on all figuring out the atomic structure, and so Rutherford did the gold foil experiment. I need to tell you, like around the 1900s, around this time, the 10-20 years before and after, there's a lot of discoveries going on. So much was going on at that point. But anyhow, one of these things was, of course, the structure of the atom as well. So what he wanted to do is he wanted to figure out where is the location of the protons, okay? Because if there is a negative, okay, which is what what J.J. Thomson's experiment said. So he said, okay, if there is negative, is it spread all around like this? Then maybe there's a positive, and that positive is all over also. Okay, so that's kind of what he was trying to figure out, is where exactly is that positive charge, because atoms are supposed to be neutral. So if they are neutral, then of course there is, positive. So now it's just about where is that positive charge. That's what he's trying to figure out. So he set up his experiment, which is called the gold foil experiment, and that what he has is gold foil all around, and the particles, sorry, the gold foil is right here, and then this is over here like a film, okay, like an X-ray film sort of thing, and then he put the sample right here. He bombarded it with positive particles. Now remember, he's trying to figure out the location of the positive particles. So here it gives you an idea of what he was expecting, okay, is that if things are distributed all around, then the positive rays that he's shining on the atoms will go straight through. That's what he was expecting. And if they go straight through, then he should see some detection right here in the film. But what happened is that some of the radiation actually bounced back, okay, and that's what's shown in this diagram also. Some of that radiation bounced back, and if that radiation is bouncing back, it means that there is kind of like a dense spot where the positive is all together, because positive will repel positive. So if there is a dense spot somewhere in the middle, then that is the one that is actually repelling that positive, okay, from there. So that is what he figured out. So what does that mean now? That means that the electrons actually are not going to be, the protons are not distributed like this amongst the electron. The protons are actually centered in one place, and the electrons are probably all out. That is kind of what he proposed, and this is his gold foil experiment. So once that is done, then you have two particles, right? So you have the protons and now you have the electrons. The last particle to be discovered was the neutron, and neutron actually is no charge, and so that's the one that's a really hard one to discover, because how do you study something that doesn't have any charge with limited instrumentation? Okay, limited, because we're talking more than 100 years ago. All right, so there's not that much instrumentation going on. So the thing that we knew, that not we, okay, I didn't have anything to do with this, but what was the intriguing part about the discovery of neutron and the fact that there is some other particle in there is the mass. Okay, because when you look at hydrogen, hydrogen has a mass of 1, which, remember I said proton is very heavy, so you're getting the mass from proton. But then when you go from hydrogen to helium, which has 2 protons, then the mass should be 2, but actually it's not. The helium actually has a mass of 4. So if helium has a mass of 4, then where's the other 2 coming from? Because 2 is coming from the proton, so where's the other 2 coming from? And it turns out that the 2 was coming from the neutron, okay, which is equal in mass as that of proton. Okay, so it took a while, but they eventually got there. This was discovered by James Chadwick about 10-15 years later, so that's finally done now. So now we have a better picture of what an atom might look like. Okay, so first of all, it is considered to be circular in nature. Then there is a dense mass in the middle, which is called the nucleus, which has the protons and the neutrons. Now remember, from what we have studied so far, protons are positive, neutrons are neutral, electrons are negative, and the negative is kind of spread all around. Okay, so that is kind of how it goes. The majority of the mass of the atom is in the center. All right, the atom actually is a really large thing, but mostly empty. Okay, so what I'm saying is that the yellow that you see all around here is really all empty space with a few electrons just kind of floating around. The nucleus is really what carries the whole weight and the mass, the weight and the mass, and it's really dense. It has all the particles in it. Okay, electrons are very light, so but they're the ones that are outside here. Okay, and so I've tried to draw it small, but if I drew it smaller than this, then you won't be able to see the nucleus. Okay, but just try to imagine a football field and a soccer ball. Okay, so that is the ratio of the atom to the nucleus. Okay, so how much empty space there is out there, that is, kind of the structure of the atom. Okay, a lot of empty space here, but anyhow, so you should know the structure, okay, and where the electrons are, where the protons are, and so on. So just a little bit of a question about, what the history of the discovery of the atom is. So go through that, okay? And again, I don't have to go through all these questions because this one is kind of simple, just about, learning who discovered what, okay? And sometimes you need to know the purpose of the experiment too, all right? So just go through this. So here it is then, the atomic mass and the atomic number. Okay, so these two numbers become really important to us because this is how we are going to go forward. All right, so atomic number is the number of protons. Remember, protons are inside the nucleus, and atomic mass is, or the mass number is the number of protons and neutrons. Okay, so what we are going to be doing is we're going to be dealing with these numbers all the time. Okay, so you need to kind of familiarize yourself with this. So let's say you have an element X, whatever X is. So the way we write these numbers is in the corners on the left-hand side, top and bottom. The top number is the mass number and the bottom number is the atomic number. If you forget which one goes where, just remember the larger number goes on the top. Okay, that's it. If you look at this, the mass number is the number of protons and neutrons, and the atomic number is the number of protons. Electrons are nowhere there, right? So you might think, oh my God, what happened? The electrons are not important. They're definitely important, okay? But first of all, in the mass, they are not significant. Their mass is so light that it is insignificant. Okay, so for example, when you weigh yourself on a balance, you would consider that, okay, I'm going to keep my wallet down or my purse down, or I might be wearing heavy shoes, but you would never think about your hair. Okay, that, oh, I need to take off my hair because my hair is really heavy. So that's not what it is. Hair is very light, and that's how electrons are. It's very light. Okay, and so we don't look at that in the mass, okay, of any kind of an atom. So that's what this is. Okay, so we have mass number, and then we have atomic number. And in the next portion, we will talk about the periodic table. So the periodic table is arranged by the atomic number, which is the number of protons. Okay, so we will look at that pretty soon. All right, in the next portion here. So in any case, this is kind of what the numbers are, and these two numbers are really what identifies the element. The identity of the element, as I said to you that we will talk about, the identity of the element is actually the number of protons. Okay, so how do you know which element you're talking about? Number of protons. Okay, so that's an important thing for us. Okay, so another thing we want to talk about before we move on from this section is isotopes. And isotopes are something that gave a little bit of a challenge to Dalton's atomic theory. So Dalton's atomic theory said that all of the atoms in an element are exactly the same, right? That was one of the theories for Dalton. And this actually turns out that it's not quite true. So elements actually have atoms that have a different mass. Okay, so just something, the mass number is just a little bit different. So if they have a little bit different mass, then what is going to be different about them? Okay, so the number of protons cannot be different, because if you change the number of protons, you change the charge also. Remember, protons are positive. So the only thing you can change is neutrons in there. Neutrons are neutral. If you change the number of neutrons, you don't change anything else except the weight. Okay, and that's exactly what is different. Okay, so which means also what? It means that the identity of the element is exactly the same. All right, so when we look at isotopes, isotopes have, like for example, if we want to look at something like carbon, so carbon can be carbon 11, carbon can be carbon 12. So what are we saying here? Carbon is still carbon, but here it has a mass number of 11, and here it has a mass number of 12, which means that carbon 11, carbon 12 have different number of neutrons in there. The protons are the same, because what? Protons make the identity of the element. So you can't change the number of protons. Okay, now can you predict how many isotopes something is going to have? So is this carbon 11, carbon 12? Well, there's carbon 13 and there's carbon 14. How would you know that? You wouldn't know that until you were working with these. Okay, so nobody knows for how many isotopes any element has. Only when you start looking at it, then you will know, okay, carbon has 4 or hydrogen has 3. If you're not studying that element, you wouldn't know that. Okay, so no one expects you to know that. You just expected to know that, yes, there are isotopes. And actually, any element is going to have isotopes. All right, so it's not just carbon or hydrogen. Any element from the periodic table, okay, is going to have isotopes in it. How do we study isotopes? Okay, how do we find those? So you do that by looking it through an instrument, and that instrument is called the mass spectrophotometer. So when you look at the mass spectrophotometer, you actually put the sample inside, and the sample gets bombarded with electrons, and then all the atoms will start kind of speeding along, and that speeding is done through a magnetic field. And so then they are analyzed by a detector, and that analysis is based on which particle is coming out first. Okay, so the first particle here, for example, for magnesium, the magnesium 24 is coming out first. That's the lightest one, because the lightest will travel the fastest, then the heavier one, and then the heaviest. Okay, so magnesium has 3 isotopes. So that is how you study isotopes, and the proportion of that is given by the height of these peaks. Okay, so then you figure out, okay, magnesium 24 is 79%, 25 is the 10%, and 26 is 11% only. So which means the majority of the mass is actually coming from magnesium 24. Okay, that's kind of what happens. So this is something that you do with instrumentation. There is no other way to figure out how many isotopes something has and what is the proportion of all of those. Okay, and once you know all of the proportion of all of these isotopes, then you can go ahead and do the calculation. So here in the calculation, what you do is you look at the isotope and you look at the percent, which is given to you over here. And this I think I have calculated for magnesium only. And then so you have the mass of each of the isotopes, and then you have the percent abundance, how much it was. Remember, 24 was 79%. So you take that percent, convert it to a number. So 11% is 11%, but actually in numbers it will be 0.11, and then you multiply that by 26, which means what? It means that 11% of magnesium 26 contributes 2.86 mass, okay, to the total mass. So you find the proportion of each of those isotopes, and once you figure that out, then you just add it up. Okay, so it's a very simple calculation to do, and so you end up coming up with 24.32. Now here's the fun part. When you look at 24.32, if you look at that at the periodic table, you will see the mass as 24.32. But 24.32 indicates that, oh, you might have a 1/3 of a particle, because remember, neutrons are equal to neutrons and protons are particles. So you can never have half a neutron, okay, or half a proton. That's never going to happen. Okay, so you either have a neutron or you don't have a neutron. Okay, so when you look at this, it kind of seems like, oh, there is a 0.3 particle. But now you're going to think like, oh, there is 0.3, so there must be isotopes. Okay, that is why there is a decimal point, because if there is no decimal point, it means you have whole numbers, right? Because you add 2 neutrons and 2 protons and you should get a total of 4, not 4.3. Okay, so I hope you see what I'm trying to say here. Okay, so that as soon as you see decimal points, you should know you're dealing with isotopes, because if there are no isotopes, then the mass number should be a whole number, because you don't have half a particle anywhere. Okay, so anyhow, this is how we calculate atomic mass, and this is how we know how many isotopes something has, any kind of an element has. Okay, all right, so that brings us to the end of this little portion where you're learning about the atomic structure, the different experiments, the particles, okay, and isotopes. We'll go on to the next one where we learn about the periodic table.